All right, so we have talked about the mass flow rate and basically how we can write the mass balance equation, and we did an example on that. So we want to talk about basically the energy balance, but we're dealing basically with the open system, and in the open systems or control volumes, there is usually a fluid passing by, which means that the fluid entering or leaving our control volume. So we have an extra energy in our system. So we have already talked about this in previous chapters, a term which is called basically flow work or flow energy. And what it means is basically how much energy is required to push a fluid inside the control volume, or basically take it out of the control volume. So that's basically called flow work or flow energy. So remember the energy balance that we had for closed systems. I'm going to rewrite it here. So delta E was basically equal to delta kinetic energy plus delta potential energy change plus delta U, right? That was for closed system. Now we have an open system or a control volume, which we have an extra energy, which is called basically the flow energy or flow work. And it's defined basically by the force. So if you assume that there is a piston pushing a volume of fluid into our control volume, which is shown here in this figure 512 here, a piston is pushing the fluid inside, and this basically fluid have a volume of V, it's at pressure P, and it has a mass M, and it's basically entering the control volume. The work required to do that is basically equal to the pressure of the fluid multiplied by the cross-sectional area of the piston, or basically the channel or tube that we are talking about. So basically that force is equal to pressure multiplied by cross-sectional area, and the workflow is basically equal to, that's the definition of work, right? Force multiplied by the length. And if that piston moves by a distance equal to L, you can see in the figure, or I can say basically that the fluid has a length of L in the system, and the force is equal to F, then F multiplied by L is going to give you the fluid work, which is equal to pressure multiplied by cross-sectional area multiplied by length, and cross-sectional area multiplied by length is equal to volume, right? So that's the volume of this fluid, and therefore we can define it as pressure multiplied by volume. So the workflow that we are talking about it here is equal to pressure multiplied by cross-sectional area, right? Now this is in kilojoule. Of course, if you want to write it per unit mass, you use basically lowercase w, and that's, sorry, this is not area, right? This is volume here. And if you want to write it in terms of basically kilojoule per kilogram, that's going to be P nu, and nu is basically a specific volume, if you remember, right? So that's going to be kilojoule per kilogram. Makes sense? And basically that's it. That's the definition of the flow work or flow energy, and that this term should be added to your energy balance equation. So if you look at the next slide, the first equation you see on the top is the energy for a closed system. You can see that kinetic energy, potential energy, internal energy, and kinetic energy is defined as velocity squared divided by 2. Potential energy G multiplied by Z. This is of course lowercase letter, so which means that the unit is kilojoule per kilogram, which is per unit mass, right? And if you want to write an equation for an open system or a control volume, we usually show the energy with theta. So theta is still the energy, but that's for an open system or control volume. And we have this extra term, which is P multiplied by nu plus the energy of a closed system, right? So that's an extra term that we have. And if you remember, we had this definition of internal energy plus flow work is equal to enthalpy, and that's why we define the enthalpy in general. So we can rewrite the energy equation for a control volume to be equal to this, which is enthalpy plus kinetic energy plus potential energy. This is the definition of the energy. So you see how different you can see at this basically picture here. The non-flowing fluids, this is number 1. Flowing systems is number 2. And you see that the difference between these two is basically the flow energy, right? So just try to write it for yourself to make sure you understand. So internal energy, kinetic energy, potential energy, that's for closed system. And theta is equal to enthalpy plus kinetic energy plus potential energy, that's for open systems or control volumes, right? So this is the energy balance for open systems and closed systems and how they are different, okay? And well, of course, we have the same relationships. If you want to write the amount of energy transport in kilojoule, you have to multiply it by mass. So that's theta is in kilojoule per kilogram again. If you multiply it by mass, then that's going to be just kilojoules, right? This is joules, sorry. So that would be kilojoule, and then if you want to write it in terms of rate, you put a dot on the top, and you have to multiply theta by m dot. So that's going to give you basically kilojoule per second or kilowatt. That's the same thing, right? Now, if you ignore the kinetic and potential energy changes, which usually most of our cases were that, we can just ignore the velocity component, the kinetic energy component, the potential energy component, and the only thing that remains is basically your enthalpy. So mass multiplied by enthalpy is going to give you the total energy. M dot multiplied by or mass flow rate multiplied by the enthalpy is going to give you the energy per time, right? Okay, so how about if you have a steady flow system? In a steady flow system, what happens? There is no basically mass accumulation inside your control volume, so the total mass of your system stays constant, which means that mass in is going to be equal to mass out. And so if you want to write the energy balance for the system, if you ignore the kinetic and potential energies, then simply you just write m dot h1 is equal to m dot h2 plus m dot h3 for this specific system, because this is the input, these two are the input. So this is going to be my energy balance for this system because there are no kinetic or potential energy changes. All right, so now we can write basically two sets of equations, right? One set is basically the mass balance. So this is for the steady flow process again. You can see this is the mass balance. Whatever comes in leaves the system. So mass in is equal to mass out. This is the definition of m dot again. Density, velocity, cross-sectional area, density, velocity, cross-sectional area, m dot 1, m dot 2, right? And if you write the energy balance, E dot in minus E dot out is the energy accumulation in the system, which is shown here by dE dt, differential of energy with respect to time. So in a steady flow process, this is equal to 0, right? And therefore, whatever energy comes in leaves your system, right? So from the energy balance definition, remember again, let me write it here. So for a closed system again, delta E was equal to delta kinetic energy, delta potential energy plus delta U, and that was equal to Q in minus Q out plus W in minus W out, right? And so for the open system, the only thing that changes is this U changes to delta H. That's the only difference that you have. Okay. All right. So this is basically the same thing. This is the energy balance for the system, and Q in, Q out, W in, W out is equal to basically the change in the kinetic energy, potential energy, and enthalpy change, right? So that's basically the same equation, except that you have enthalpy here instead of U, or internal energy. Okay, so if you basically write the equations with the sign convention that we talked about it, that heat input and work outputs are positive. So this is very important convention. Make sure you understand this. Okay, so if you write it that way, then if you have a heat input, you put basically, if you have heat input, then this will be positive heat input. And if your system does some work, then that's going to be positive again, right? System does work. Sorry for my handwriting, but that's how you basically do it, right? So Q minus W is equal to change in energy from exit to inlet of your system. Okay. All right, so cool. So this is what we have so far. I think you'll understand it better if we do an example. Most of engineering devices use the steady flow system, so the problem is a little bit more simplified than just general equations that we talked about it. So in next slide or next video, we will talk about and we will solve a problem, an example problem.